Welcome back to The Explainer. We're jumping right in today because we've got a deep, technical teardown of something that is literally rewiring the internet's backend. We're talking about on-chain identity. Specifically, we're pitting two totally different architectural approaches against each other. In one corner, the highly anticipated evolution of the Ethereum name service, ENS v2. In the other, this radically dense Bitpacked protocol known as LNA-33X. Its mapped registries versus self-mapping geometries, and the implications for how we build decentralized infrastructure, honestly, they're massive. So think about this for a second. When you register an on-chain identity, does your name just point to a record somewhere else that holds the truth? Or is the name itself the actual undeniable truth? Keep that philosophical divide in your head as we go through this. Are we building highly organized digital filing cabinets with mapped architectures, or are we engineering self-mapping Bitpacked DNA that natively commands the machine?
Here is our agenda for today. 1. The namespace dilemma. 2. ENS v2, hierarchical registries. 3. Gas-optimized ERC1155 singleton. 4. LN-33X Bitpacked geometry. 5. Authority via semantic containment. And 6. Mapped versus self-mapping architecture. Let's get right into it.
Section 1. The namespace dilemma. Our sources point out a pretty stark reality. The difficult problem in naming isn't issuing strings, it's achieving universal resolvability. If you've ever bought a domain that only works on one specific app, you know exactly how frustrating that is. A name that resolves inside a single application is just a walled garden. It's not infrastructure. The early flat registries, like ENS v1, were elegant for their time, sure, but they hit a wall. Everything sat in one monolithic contract. So if a parent name expired, you got stuck with these active zombie records for subnames. True public infrastructure needs complex architectures to kill those bottlenecks, boost flexibility, and actually keep gas costs down. Which brings us to Section 2. ENS v2, hierarchical registries. So a hierarchical registry is basically a ground-up reimagining of the protocol. Instead of that single, flat smart contract making the rules for everyone, ENS v2 lets every single name define its own unique registry and resolver for managing subnames. Think of it like a massive, highly organized digital filing cabinet where you have absolute granular control over your subdomains. For instance, if a DAO wants to instantly reset hundreds of membership subnames at the end of a governance period, boom, they just deploy a fresh registry for their main domain. It's instant subtree management, and it's a huge shift. Now, because we ditched the single flat database, resolution has to happen recursively. Under the hood, it's a simple flow. An application queries the universal resolver first. That's step 1, your single entry point. Step 2, that resolver checks the top-level domain registry, something like .eth. Step 3, it moves down to the specific domain registry. And finally, step 4, it extracts the data from the resolver contract. The user never sees the complexity of this tree traversal, but structurally, it functions as a highly modular directed graph. Section 3. Gas-optimized ERC-155 singleton tokens. 60%. That is the massive gas savings you get using the ERC-1155 standards batch operations compared to deploying individual ERC-721 tokens. When you're dealing with an entire hierarchy of names and subdomains, executing transfers one by one, yeah, that's prohibitively expensive. Nobody wants to pay that kind of gas. So the ERC-1155 multi-token standard swoops in, allowing developers to move multiple token IDs in a single transaction frame, which just completely slashes blockchain congestion. To actually pull this off, ENS v2 uses a very specific implementation, the ERC-1155 singleton. Normally, ERC-1155s manage multiple copies of tokens, right? But identities absolutely have to be unique, so this singleton pattern enforces exactly one token per ID. And because that supply is mathematically locked at 1, the smart contract doesn't have to waste expensive compute power constantly tracking and updating balances. It treats subdomains as standalone NFTs with the raw efficiency of an 1155, all while maintaining full compatibility with legacy NFT marketplaces. It's incredibly efficient bookkeeping. All right, Section 4, LNA-33X Bitpacked Geometry. Let's totally pivot and look at the literal anatomy of an LNA-33X identifier under the ERC-7827 protocol. Instead of relying on a web of external registry contracts like ENS, this architecture engineers identity at the absolute lowest foundational level. It takes a single 32-byte EVN word, which is literally the standard base unit of data on Ethereum, and strictly partitions it into 3 clinical segments:
a 3-byte link, a 3-byte nonce, and 26 bytes of ASCII.
Let's actually break that down, because this acts like physical on-chain DNA. The 3-byte link points to a previous shard's nonce, which lets the system bypass standard limits and string together long characters for complex hierarchical handles. Then you have the 3-byte nonce. This is a monotonic, incrementing value, meaning it literally only ever goes up. That ensures every realization is a fixed, final point in the historical record. Finally, the 26-byte ASCII segment stores the actual human-readable payload. Because of this bit-perfect integer geometry, the name isn't just pointing to a coordinate somewhere else. The name is the active coordinate. And that leads us to a very important number, 0. The source materials detail how this protocol strictly pivots to a LIFO, last in, first out, JSON state structure. Think of it kind of like a stack of plates. Why does this matter? Well, because the very last item added is the first one to come out, you unlock incredibly efficient single-entry bookkeeping. A client only ever needs to query index 0 to get an immediate, definitive proof of state. No searching through a massive database to find the current truth, it's right there on top.
Section 5. Authority via semantic containment.
This brings us to a really fascinating concept, semantic containment. This is utilized by internal projects like Island Hats, and it fundamentally flips how access control works. In traditional systems, authority flows through structural inheritance, right? Explicit links mapped out in a smart contract tree. But with semantic containment, authority is derived simply by directly scanning the ASCII prefixes stored right inside that LNA-33X payload we were just talking about.
Basically, possession equals authority. If you hold the agent namespace token, you automatically have the mathematical authority to realize child shards. Say, minting something like daemon.agent. Because the ASCII payload literally contains its own hierarchy, this internal scanning creates O of 1 complexity. That means authority is verified instantly, no matter how gigantic the system gets. The token natively commands the hardware logic, completely bypassing any need to check an external mapper or resolver. It is 100% self-contained.
Section 6. Mapped versus self-mapping architecture. Let's put these two head-to-head. On the ENS v2 side, we've got an addressing scheme based on hierarchical registries, so highly flexible modular trees of contracts. LNA-33X, on the other hand, uses a hyperdense bitpacked ID inside a single 32-byte word. For resolution, ENS relies on an external resolver to fetch the data, while LNA-33X is entirely self-resolving via semantic containment. And finally, looking at the token standard, ENS v2 leverages the GAS-optimized ERC1155 singleton, whereas LNA-33X utilizes what the sources call a 3-shard stack, anchoring root authority, collective permissions, and individual coordinates. Which brings us right back to our core philosophical divergence. ENS v2 is a brilliantly powerful indirect mapper. It's a way to organize digital files requiring external contracts to link symbolic, human-readable names to a machine state. LNA-33X is active on-chain DNA. The name itself is the coordinate, and the payload, the whole shebang. No external mapping layer required whatsoever. But despite these radically different architectural approaches, they both share a singular goal. As our sources remind us, a name that works across applications, networks, and contexts starts to look a lot more like infrastructure. Whether it's through the elegant registry trees of ENS v2 or the clinical integer geometry of LNA-33X, both of these protocols are successfully pouring the concrete for the decentralized public infrastructure of the future. They are finally moving us past those isolated walled gardens and into a universe of true universal resolvability. So, I'll leave you with this final thought. We've seen exactly how mapped hierarchies and bitpacked geometries are completely reshaping the nature of digital truth and on-chain identity. The tools for unprecedented scalability and verifiable authority are already here. So the question is, with mapped hierarchies and bitpacked geometries reshaping digital truth, how will you architect your next Web3 protocol? Are you going to build a registry, or are you going to pack a bit? Thanks for joining me for this explainer. Keep building, and I'll see you next time.